I inserted this here at the beginning because I cut it short later on in the video, but it's the actual elevation, GPS elevation layout for LIGO coordinates. And it's funny how Blue left this page out. The only thing that matches with his elevations is the beginning and the end of the southwest arm, but everything else is different. But it talks about the Lambert grid system conversion. It talks about the least squares adjustments on the elevations, basically how they approximate or just a way to adjust it to your model out in the field. Look over it. The pages, it's all in there. This is not provable ball.
This is a satellite view of the Livingston site.
What we're going to go over in this video, I'm going to try and keep it short, is Blue Marble Science's LIGO proof of a globe. Okay, I'm going to show you that he's absolutely wrong. Does not prove a globe, and there's a fatal flaw I think he's overlooking. I'm going to show some conflicting elevations in the plans that he routed us to, and the ones he got his information from. Let's get into it.
This arm is identified as the southwest arm, and it extends 13,100 feet. That's about 2.48 miles or 4 kilometers. The second arm also extends 13,100 feet, and it's referred to as the southeast arm, and it forms a nearly perfect right angle with the first.
Whoa. What does he mean, a nearly perfect right angle? For the interferometer to be as accurate as they're claiming, or for it to even work, wouldn't it have to be a perfect right angle? Now, I could think of one way that it would be a nearly perfect right angle, as if in reality it is a perfect right angle, but projected on their globe, it's just nearly a perfect right angle, which makes perfect sense to me. But let's hear some more.
Arm. The laser beams are fired through tubes that are about 4 feet or 1.2 meters in diameter.
So 4 feet, okay? Now, the measurements that he gives, which I'm going to show here in a minute, he has the southwest arm, okay? The middle of the southwest arm is 1 foot lower than the beginning and the end, okay? Making that the tangent, okay? Which is, you know, it has to be, unless you could think of another way they could fire a straight line elevation beginning and end level and lower in the middle. I agree with him on that. The middle of the southwest arm has to be the tangent. It's a foot lower, but that means that there's 6 inches of play on each side to have a straight path. So if the tubes are 4 foot, you know, the tubes really only needed to be 1 foot for it to work on a flat Earth. So they're 4 times the necessary size to have a line of sight on a flat Earth. So that's the arm he says kills the flat Earth, and I'm showing right out of the gate that that's not necessarily true. But I've got better than that. So stick around.
Go to the website you see listed, and I'll have a link to that in the description. You'll see this page. And if you go to the tab that says Civil, right there, and click on that, you'll get a list of these drawings. Now, the one we're going to look at first is this one. It is drawing LA-C-001 Rev 2. And it looks like this. You'll notice on these drawings that you'll find a key plan right down here in the lower right corner. And that
key plan with no detail on it. And I'm going to show you a key plan with detail, listing the LIGO stations numbered. But
plan tells you what section of which tube you're looking at. That cross-hatched section is what this drawing pertains to. So you can see this drawing starts at the vertex, goes out 1,400 feet, and it gives us elevations every 100 feet. So if we go through the drawing set, we can pick out these elevations. For the southwest arm,
I came up with going through the plans for the southwest arm. I mean, he just writes it on there and just. But I got you know, I didn't maybe I'll look at it again, but I lined up with the southwest arm, but the southeast arm, I had a I thought there was a discrepancy, but maybe not, maybe not. Let's I'll give him credit for that and follow with him because, like I said, the northeast arm or northwest arm was it did line up, but there's a fatal flaw in all this, okay, and it's gonna become apparent. But okay, so if the tangent is the middle of the southwest arm, okay, so I would say that the beginning and the end, okay, you would say that on a globe, if they're both 64 foot, okay, then one of them is dropping 4 inches. One of them's 4 inches lower, depending on the one you're standing at. But the tangent being in the middle, okay, is how they get around that, okay. Like they like to combine the two models sometimes when it suits them, or use one or the other, depending on which one suits them. But anyway, they're stuck right here. That has got to be the tangent, and which he states, and I agree with him on that. Okay, so that means everywhere else, wherever you are, is an equal elevation is going to be 4 inches down after 2.5 miles. Okay, so if you look at the southeast arm, the it's dropping down 4 inches from the beginning at the vertex to the end. So that means it's dropping down 8 inches. Okay, you can't change your angle again. Okay, you already changed it. I mean, you could try and change it, doesn't matter. Your tangent was on the southwest arm. So for it to be the same type of layout, the middle, for you to change the angle, then the middle would have to be higher again. Okay? But you see, I hope y'all understand what I'm saying. In other words, the angle that they have set up LIGO, okay, is with the tangent in the middle of the southwest arm. So in other words, if you are standing in the middle, looking toward the end of the southwest arm, it's angled down a little bit. Okay, that's what that means. Okay, so that's how they established the elevation, pretty much to begin with. But the common point is the vertex, where the two arms meet. Okay, so if you look at the end of the other arm, it's 4 inches down, which means on a ball it's 8 inches. I mean 4 foot. I keep saying inches. 4 foot down, which means on a ball it would be 8. And really, it would be even worse than that, because you're angling up from the center of the southwest arm. But I'll stick to their dimensions and say 8 foot. But that means they're borderline even having a straight shot. I don't think they're right on the edge of having a straight shot with a 4 foot tube. Okay, and I'm going to show my conflicting evidence here shortly.
And the same thing applies to the southeast arm. In a separate document titled Precision Alignment of the LIGO 4-kilometer Arms Using Dual Frequency Differential GPS, and I'll leave a link to that in the description as well.
See that right there? Now he's talking reality. Okay, differential GPS. Okay, differential is always going to be the best accuracy they can get, whether it's differential with the laser, differential GPS, differential with the light, or an auto level. It's always going to be the best because you got the middle and then you shoot out both ways. Okay, and that's always going to be the most accurate way. Any surveyor who knows what they're doing will tell you that. And that's how, okay, they could pretty much lay this thing out all they want. In reality, they're going to go off of one benchmark and make adjustments accordingly, okay, through differential leveling. And it even says it on the elevation profile itself. And I'm going to show that. So bear with me.
plane that these two arms form. And it essentially is telling us that that plane is tangent to the WGS-84 model at some point within the triangle formed by the two arms. Now, I've assumed that that tangent point is somewhere near the center of the southwest arm, and I'll show you why. This is the satellite view of the LIGO arms again, and this is the information, the elevation data that we got from the as-built drawings. When we plot that data on this satellite view, it looks like this. Now notice on the southwest arm that the two end elevations of 64.09 feet and 64.12 feet are very nearly identical. The center elevation, however, is about a foot low at 63 feet. That makes perfect sense if the plane formed by the two arms of LIGO is tangent to the WGS-84, somewhere near the center point of that west arm. Obviously, that does not...
So that's his numbers right there. Now you see how the tangent, okay, the 64.12 feet is the common, so that's the center, that's the vertex, okay? And then you have 63, which is a 1 foot drop in the middle of the southwest arm I was referring to. Then it goes back up to 64 foot at the end. So that's got to be the tangent, meaning the 64 down to the 60 foot at the end of the southeast arm would be an 8 foot drop. They didn't think of that one, did they? What they did is they laid this damn thing out on a program. And now he keeps saying as built. So the elevation profile I'm going to show you is the actual elevation GPS layout. It's, like I said, it's got some conflicting and some similar information, which is no coincidence. So they're saying as built. He's saying as built. So what? So this is what it wound up being after they built it. I thought these were the plans to execute the damn thing. Was it already built? This is as built or per plan? You know, there's just too many. I don't know. Just stick around. I'm going to show you the other profiles. One other thing. Why aren't the measurements like lining up exact? You know, I guess that's their margin of error. In other words, it doesn't have to be perfect as long as it fits reasonably in that 4 foot tube. You know, you're talking an arc second from the top to the bottom of the tube, if that. And I'm going to go into that too.
Looking at this in AutoCAD, here is the southwest arm. And we'll just have a quick look. Here's the vertex at an elevation of 64.12 feet. Here is the end section, the end station at 64.
Anyway, I showed all this to show you that all they did is basically they're just showing AutoCAD. That's the measurements he gave, you know. That's the measurements that are on the plan. His AutoCAD of how it would work on a ball, okay? The problem is, like I said earlier, it would work on a flat earth, even with your little recess in the middle of the southwest arm, because like I said, it's only 6 inches per end to make it an exact shot, okay? And I was going to play a little bit more of this, but you get the picture. It's just going to show AutoCAD. So basically, it lines up perfect with the plans. Even the part that he got the elevations from is an AutoCAD layout. But I'm going to skip through. Blue says that it won't work on a flat earth because the 1 foot drop in the middle of the southwest arm. Okay, so that's 6 inches each way. So I went to the triangle calculator. That comes out to 0.00004 degrees, which is 14/100ths of 1 arc second. So 14/100ths of 1 arc second. He's going to tell me that wouldn't work on a flat earth LIGO wouldn't work on a flat earth. That's crazy. It's a 4-foot tube. They would only need like 13 inches to have line of sight, and they have a 4-foot tube. So anyway, I show the elevation page in the plans, the actual elevation page, and it matches the southwest arm as far as the beginning and the end. The middle is a little bit different, but it talks about, read the details for the elevations and the GPS information. It talks about how they use the Lambert grid and the Louisiana grid systems, and how they use least squared adjustments. So that's pretty much field adjustments, and pretty much, giving it leeway to match a model, basically, is what it boils down to. You look in and see what you come up with, but LIGO does not prove a globe. I'm sorry.